This is going to be a walkthrough of a photoelectric effect problem that you can see at the top of the screen here that says that electrons with a kinetic energy of 6.023 times 10 to the fourth joules per mole are evolved from the surface of metal when exposed to photons with a wavelength of 600 nanometers. So what is the minimum amount of energy required to remove an electron from the metal atom? Now, we've got a few different terms here that people might find confusing, and I always like diagrams to help with my understanding of things. So let me draw the surface of this metal, the light that's coming in and striking the metal, and then the electrons that are being ejected. And let's label these as some of the information we've been given. So let's start off with the first piece of information that's given is that the electrons that are ejected have a kinetic energy of 6.023 times 10 to the fourth joules per mole. So their energy, their kinetic energy, is 6.023 times 10 to the fourth joules per mole of electrons, right? I'll just add that little extra note there so we don't forget that per mole in this case, because we're talking about particles here, is mole of electrons, right? It's per mole of electrons. Okay? Moving on in the problem, it says that this is happening, right? These electrons are ejected with this kinetic energy when they're exposed to photons with a wavelength of 600 nanometers. So this means the wavelength of the light coming in is 600 nanometers. That's causing these electrons to eject with this energy. So note here, if you've watched any of my other videos on the photoelectric effect, this problem's kind of similar to the first video that I recorded, where we were trying to solve for what the work function would be of the metal. So note here, that is what this last statement means. What is the minimum amount of energy required to remove an electron from the metal? That is the definition of work function or binding energy. So part of this word problem is kind of testing your vocab a little bit, like testing your understanding of the concepts. Do you know what it means by this statement, right? That statement basically just means, what's the binding energy? What's the work function of this metal? How much energy do we need to remove an electron from the metal atom? And really, what's the minimum amount of energy that we need? Because we know that the light coming in here can deliver more energy than is needed to eject an electron. That's how we end up with kinetic energy for the electrons themselves. Because remember, this value in pink here, this kinetic energy amount, that's the amount that's left over after the photons coming in transfer their energy to an electron and that electron gets ejected. So we want to keep in mind again how all three of these energies are related to each other, right? This green arrow that I have over here with the wavelength of 600 nanometers, that correlates with the light. And so we're going to have some energy of the light that we can calculate using this 600 nanometers. And that's basically going to be for each photon that comes in. And then that photon with that energy of the light transfers all of that energy over to the electron in the metal. And part of that energy goes towards ejecting the electron, so the work function, and then whatever remains of that energy goes towards the motion of the electron, the speed of the electron. And we refer to that as the kinetic energy, and that kinetic energy can also be used to talk about the velocity of that electron. Now in this problem, since we're just given kinetic energy, we're never going to have to consider velocity here, but we do want to remember that those are the terms that are related to this final energy portion that we have in this whole situation. Now, what we're going to eventually want to be able to do is look at the relationship between these three values. So let me remind you guys of what that relationship looks like. Remember, the energy of the light coming in represents the total amount of energy that's available for this process. And when that energy for that photon, right, that energy of that light, gets transferred to an electron, it goes into two places. It first goes towards the work function, towards the binding energy, and that's that energy that we're going to need to eject the electron. So some of that energy from the light gets used to eject the electron. And then the other portion that this energy goes towards is the kinetic energy of the electron. So the work function plus the leftover kinetic energy should tell us how much energy we had initially coming in for the light. But this relationship here can be rearranged to solve for any value that we want to solve for. So in this situation, if the goal is to solve for the work function, I'm rearranging this equation to note that the energy of the light minus the excess energy that's left over, right, the kinetic energy, should give me the work function. So I basically want to solve for what is the energy of the light coming in, what is the kinetic energy, and then subtract those two to get what the work function is. Now, what makes this problem a little bit tricky is that, remember, these equations, when we use them, always have to be calculated per particle. So when we're talking about the energy of the light here, we're talking about the energy, per photon. And when we're talking about the kinetic energy, we're talking about the energy that's left over per electron. And when we're talking about the binding energy, we're talking about the amount that's needed to eject each electron, right? So that's also a per electron amount. Why is this problematic? Well, this kinetic energy per electron, that's not what we have given in the problem, right? We've got the amount per mole of electrons. So the very first thing we want to do is take this value, 6.023 times 10 to the 4th joules, and represent it as a ratio, because really this is the amount of energy per 1 mole of electrons. And I want to recognize that I really want to get the value per 1 electron. So on the bottom here, I want to have units of electrons. And I want to get rid of the per mole of electrons. So on the top, I want to have 1 mole of electrons so that my moles are going to cancel out. Well, in this ratio, what makes sense here, right? What is 1 mole of electrons? How many electrons is that? Well, that's Avogadro's number of electrons, right? So 6.022 times 10 to the 23rd. Okay, so if I divide the value I was given by Avogadro's number, that's going to get me my amount of energy per electron in this problem. And the way I designed this problem is so that we get kind of a nice number here, which is that it's about 1 times 10 to the negative 19th joules. And again, remember, this is per electron for the kinetic energy that's left over. Okay, so now that we have this value per electron, we can go ahead and use, right, the equation, this equation up here. And so I'm going to set that up. So work function is equal to, now we have the first term is energy of the light per photon. So remember, in green here, this energy of the light, that comes from the hc over lambda equation if we're given wavelength, which we are in this case. But you could also, if you were given frequency here instead, you could use h nu. So just remember, there's 2 different versions of that light equation. You pick which one you're going to use based off of what information you're given. So since we're given wavelength in this problem, I'm going to use hc over lambda. So hc over lambda is going to go there. And then my kinetic energy is what I'm going to subtract from that value. So minus the kinetic energy. And I've solved for that now per electron, so I can go ahead and put that value in. Right, the number of joules per electron. Okay. So we're going to keep plugging and chugging here. So I don't have my work function yet. I got to plug and chug into this light equation. So H is going to be 6.626 times 10 to the negative 34th joules seconds. Speed of light is going to be 2.998 times 10 to the 8th meters per second. And then on the bottom, I want to use the 600 nanometer wavelength, but I can't plug in nanometers because the value I plug in has to have units that match my constants. So if I have meters in the speed of light, I need to have meters on the bottom. So remember my little trick, right? If I've got a unit with a prefix, I can swap out that prefix for what that prefix stands for and keep everything else the same. So I'm going to keep the 600, but for the nano, I'm going to swap that out with what nano stands for, which is times 10 to the negative 9th. And then I'm going to keep the meters, right? So 600 nanometers up here becomes 600 times 10 to the negative 9th meters, okay? And then from that, we're going to subtract again this 1.00 times 10 to the negative 19th joules. All right, so let's see what this part in green ends up equaling, because that's always good to consider here. So let me type this into my calculator. So we've got 6.626 times 10 to the negative 34th times 2.998 times 10 to the 8th divided by 600 times 10 to the negative 9th. And we get a value here for the energy of those 600 nanometer photons of 3.31 times 10 to the negative 19th joules, right? And again, that's per photon. And we're going to subtract from that the amount of energy that's left over when these photons get ejected, which is 1 times 10 to the negative 19th joules, oops, per electron, right? And so if I go ahead and solve that out, 3.31 times 10 to the negative 19th, note that that is a larger value, which is important here because in order for an electron to be ejected with some amount left over, we need to have a pretty big energy for the photons coming in. So notice that this value is much greater than the amount that's left over, as it should be, right? Because this amount per electron is actually coming out of this total energy that we're starting with in the problem. When we subtract these two, though, we are going to get a final value of about, oops, change back to blue here. I'm going to get a final value of about 2.3 times 10 to the negative 19th joules. And remember, that's per particle, so per electron in this case, since we're talking about the binding energy or work function, right? So putting these three energies together, remember this thing in green, that's the amount of energy that comes in. That's the total energy we have available. When that photon strikes the surface of the metal and transfers all its energy over to the electron, this amount, 2.3 times 10 to the negative 19th joules, is what's used to eject the electron. So we take this amount away from our 3.31 times 10 to the negative 19th joules because that's the amount we need to get the electron to eject. And then, because this amount that's needed to eject the electron is less than the amount we started with, we have this 1 times 10 to the negative 19th joules left over. And so that 1 times 10 to the negative 19th joules for each electron ends up becoming its kinetic energy, and it gives that electron some velocity. And if you wanted to, you could take this energy, recognize that it comes from the equation 1/2 equals m, or 1/2 mv squared, and you could solve for the velocity of those electrons, right? So keep in mind, right, this is the value that ends up being used to solve for velocity in certain problems. This problem's not asking us to do that, though. All we needed to do was determine the work function, so we have done that here. All right, I think that's it for that one.